All right, so today we'll learn the second type of multiplication or product with vectors. So there was the dot product, which produces an answer that's just a number. And then there's a cross product, and the cross product produces an answer that's a vector perpendicular to the original two vectors. And here's the wonderful formula for the cross product. It's going to be the length of u, the length of v, sine of theta, and then this n with the hat, that's the unit vector perpendicular to both u and v. So no matter where you have two vectors, right? If I put my hands together like this to represent two vectors in 3 dimensions, no matter where they are, you can always imagine something coming out perpendicular to them. And it's either going to come out perpendicular to them up or perpendicular to them down. And you might have had the right-hand rule in physics, and we'll do something similar to this to figure out which way the vector goes. So if you have two vectors in 3 dimensions, there's some plane in 2 dimensions where they're sitting. So I mean, if I have it in 3 dimensions, I can put a piece of paper and they would be on that piece of paper at some angle. And I've got that in that picture there. Let's say we've got u and v in that direction. So when finding the cross product, the answer is going to be perpendicular, but either pointed up out of the paper or down into the paper. And the way that you can figure it out with the right-hand rule is you draw both of your vectors, u and v, and you put your hand on the first vector, pointing in the direction of the vector. So here in the diagram, I've got my hand pointing. It has to be your right hand. If you try this with your left hand, it goes wrong. Then you need to move your bottom 3 fingers towards the other vector. So if I start on u, I can move my bottom 3 fingers towards v, and my thumb then points up, and that would be an example of that vector shooting out of the paper. If I started on v, and my thumb is pointing up, I cannot bend my, don't even come up here and try. I cannot bend my 3 fingers back. The only way I could bend my 3 fingers back is if I pointed this way and turn them down. This would cause it to go into. So this is the right-hand rule, how it works. I'm going to give you a different version of the right-hand rule as well, because I sometimes find with the right-hand rule, all of a sudden I'm watching a quiz or test and everybody's like doing weird hand motions, trying to put their, like they're really concentrating on putting their hands on that vector and figuring out what's going on. So I sometimes, this other way, I've got it here with a wrench, but I sometimes think of it as the toothpaste rule, because usually when I talk to a class, most of them have at least brushed their teeth once in their lifetime. So they have this experience with toothpaste. And in this first one, if you imagine this is your toothpaste tube, right? Here's the lid of your toothpaste tube. Ooh, I don't know if I'm going off into, there's 3-dimensional. The lid is pointed out to, that looks like an eye. I don't know. I've brushed my teeth, but I'm not good at drawing toothpaste. But if you imagine that, and from U to V, if you turned your toothpaste cap in that direction, you're holding it and you turn it in that, would it get looser or would it get tighter? It would get looser. So you've done toothpaste enough that you can imagine that. And if it got looser, would not the lid come towards you? And if you turned it if you had your toothpaste facing you and you turned it this way from V to U, would not your toothpaste cap get tighter? So I use toothpaste because there are, right, if like my wrench example is not the best because there are sometimes there's machines that have reverse threads. Usually righty is tighty and lefty is loosey, but there are some machines that switch that up just for certain reasons. I'm not sure. Can't give you a practical reason. So that could be another way to think about which way the vector's going. If you turn from U to V and it loosens the cap of your toothpaste, it's going to be coming out towards you. If you turn from U to V and it tightens the cap, it's going to be the vector's going to be pointed inwards. So that's the right-hand rule, or the toothpaste rule. You can use it either way. So U cross V is not equal to V cross U. Because one will be a vector in this direction out, and the other would be the vector in the direction inwards. So they're opposite vectors, but not equal. Which means, since they're opposite vectors, anytime that you want, if you wanted to do V cross U instead of U cross V, you could do that by taking a negative out in front. So this is kind of an important property of the cross product. All right, here's our first example. The angle between two vectors U and V on a flat surface is 50 degrees. If the length of U is 10 and the length of V is 20, let's find both of these cross products, U cross V and V cross U. So it's just the length of U, length of V, sine of theta times the unit vector perpendicular. And in this one, I'm going from U cross V, so I'm going U to V. That tighten your toothpaste cap or loosen it. Right, so if it's loosening it, then it's going to be coming up. Lefty loosey, it's going to the left. So we're going to get our answer, but then we have to write a statement where N is in the direction outwards from the paper. And V cross U, of course, would be exactly the same numbers, but that would be in the direction into the paper. And if you want to practice your right-hand rule, right, U to V, oh, that one I can do.
Or if you follow the curve of the fingers, that's perfect.
Yeah, you can curve your fingers. Yes.
In this case, would that ending vector just be like 0, 0, 1? Like maybe that's a column.
It is outwards of, like, if this, since it's on a paper, yes, because the outwards would be the Z vector, and it would be 0, 0, 1 now. But sometimes you've got your 3 dimensions going to be on some kind of weird angle, right? So it's not always going to be 0, 0, 1.
Okay.
But if your two original vectors are in 2 dimensions, yes, your third vector will be going upwards in the Z direction or downwards. So then there's some, like, again, the crazy thing about vectors is they've got the dot product, they've got the cross product, and they realize there are some crazy applications that would have been harder using our regular math that now become super simple. And one of them is the area of a parallelogram. So the area of a parallelogram is given by the following formula. It's just base times height. Area of a parallelogram is the same as the area of a rectangle. In fact, you can see that if I draw this part section there, and I just happen to move it over to here, it makes a perfect rectangle. So the formula for an area of a parallelogram is the same base times height like a rectangle, because you could just cut off one piece, slide it over, make that perfect rectangle. So we have two vectors, u and v. It's like saying I have the origin here, and a point here, and a point here. And with those 2 points, I could make a parallelogram. So if I wanted to find the area of that parallelogram using regular math, I would have to figure out those lengths, because I'll need the length of u. I need to find the height, and if I know theta and I know this length, then I can use sine opposite over hypotenuse right here to solve for h. Then if my area is base times height, and I substitute these things in, well then my base is just the length of u, and my height was the length of v times sine of theta, and we notice, hey, this is just the cross product's magnitude. Because the cross product would have an extra n hat there, which has a length of 1. So if we find the length of this, that is just the magnitude of the cross product, which will come in nicely when we learn the Cartesian form of the cross product. So here's our new formula for the area of a parallelogram. The area of the parallelogram is just the length or the magnitude of the cross product. So here's our example from before. In our example before, we found out the cross product was 153.209 n. This is given that this length was 10, this length was 20, obviously drawn beautifully to scale, but don't look too closely. And then we find the length of that was just going to be 153.209. Since it is an area, the units, whatever units we'd have would be units squared. So if these units were centimeters, then this area would be centimeters squared. Yes.
Where are we still getting the unit vector from?
Where are we getting that from? Well, this one right here was from this
I
original
see. It's
equation.
before we take the magnitude. I
Right.
see.
And then once we take the magnitude, that
Then we
unit
ignore
vector
the
just
unit
goes away.
vector. Yeah.
Yes. Yeah. So finding the cross product would have the unit vector, and then applying this formula to this would just get rid of the unit vector because its length is 1. Now, the cross product you're going to remember the cross product because it is very, very similar to things that you see with your discriminant, with your discriminant when you did matrices. So this is, look at the answers that we have, okay? The cross product with two vectors in 3 dimensions. To find the first one, I ignore the numbers in the first one. Get a number there, A2, B3 minus A3, B2. Doesn't that remind you of finding the discriminant of your matrices? The second one, ignore the second ones. Look at my cross product here. But this one you'll notice, I sometimes just write it as the negative of A1, B3 minus B1, A3. It sort of goes plus minus plus. Which also happened in our discriminant using the one formula with a 3x3. And then the last one, if you ignore the last row and just do the discriminant here, A1, B2 minus B1, A2. So that's the pattern that's happened. And one way to remember the cross product in the Cartesian form. The other way is to write out your IJK components like this and draw arrows. I'm going to show you that with these actual numbers. So we've got the vectors u and the vectors v, and we're asked to do the cross product. So we could do the pattern that I just showed you, which is ignore that and do the little discriminant. Then ignore the middle one, do the discriminant, but make that one negative. Or if you write IJK, IJK, I is of course 2, -1, 5, 2, -1, 5 for the blue one. And -6, 3, 8, -6, 3, 8 for the green one. Then you make your diagonals go through I, J, and K in one direction, and I, J, and K in the other direction. And the reason you write them out twice is just so that your diagonals have enough numbers to go through. You see this red diagonal that went through K? I could have done it here through K. It has the exact same numbers. So as long as you do I, J, and K once in one direction, I actually probably would, if I would write this again, I'd do I, J, and K. Probably do the last K rather than the first K, but it doesn't matter. We get these numbers. The negative numbers are going to be 6, 15, and 6 when I multiply them. The positive numbers in purple are -8, -30, and 6. And just like matrices again, the ones on the right, you add them all up. The ones on the left, you add them all up, and you do the purple numbers minus the red numbers in the end. Okay? And for your I coordinate, oh yeah, you don't add them up. Sorry, that's not, now I'm thinking matrix. For your I coordinate, you go to your I coordinate, the purple was -8, the red was 15, -8 minus 15 is your I coordinate. Use your J arrows to find your J coordinate and your K arrows to find your K coordinate, and we get our cross product. And now our cross product is a vector.
Is that vector perpendicular?
That vector would be perpendicular to both the original two. So if I did the dot product with those two, how do we know what the dot product if two things are perpendicular?
The dot product is 0.
if the dot product is 0. And if you did the dot product with both of those vectors and this new vector, you would get 0 both times. Now this isn't a unit vector. If we found out the length of this, we could write that length out in front and write the unit vector afterwards. All right, and this is the other method that I showed you. Right, ignore the first one. Think of the matrix at the bottom and do its determinant. Ignore the middle rows. Think of what's left as the vector, as a matrix B, and do its determinant. The middle one will be negative. The IJK method works really nice. Now, when we put this all together, if we bring this back to the idea of the area of a parallelogram, we just took 2 points in 3 dimensions. It was not hard to find the cross product using the Cartesian method. Either of these techniques work out relatively easy. It would not be hard to find the length of that 3-dimensional vector. A squared plus b squared plus c squared and the square root. And in 3 dimensions, we just made a parallelogram and could easily find its area, which is quite amazing. In 2 dimensions, if I gave you 2 lengths, I think you could do the math and figure out the height and use our old skills and find the area not too bad. But the same concept in 3 dimensions all of a sudden would become very difficult. And this makes it really, really simple. And I think that's one of the beauties of math. As we get to more and more complicated math, it makes previous things simpler than ever before. It's like all the calculus that we did, now the max-min problems that were tough in grade 11 pre-calculus, the derivative you solve like, oh, super fast. But you had to learn all that complicated stuff to get that new shortcut. So when we put all of those answers together, we would also get our cross product answer. And the cross product is always a vector. So now you have 2 different things for the cross product. I find working with the Cartesian form is usually easier and more helpful than the formula, the u, the v, and the sine theta. So here we have 2 vectors, and we know their cross product, and we want to find the value of x. So if you use either the determinant method or the IJK method, I don't know if you noticed here, but I pretty much did. No. playing around with colors. Oh yeah. This is the method I did. I covered those. I did my determinant. 3x minus 4. Was that hard? Then for the second one, I covered these. I did my determinant. 7x minus 3. I put it in brackets, put a negative out in front. Second one's always negative. And the third one, I covered these ones. I did my determinant. 28 minus 9. And I could use either the first one or the second one to figure out what x is. The 3x minus 4 has to equal 2. That works when x is 2. I double check. Does that still work with the second one? Because it could have been a mistake. They say the cross product is, and it's actually not true. But in this case, x equals 2 works. I think I like the determinant method because the IJK method, I have to write out so much stuff before I can start it. And this one I can just sort of cover things and see what's left. So if we consider these two vectors, find the area of the parallelogram and find the angle between them. So we've got two vectors in 3 dimensions. Which I find if I took a point in space and I try to draw this out, this is going -6 in the x direction. My y direction's towards me, 3 here and 4 up. Okay, there's the vector. See it? That's -6, 3, 4. Okay, and 9 here, 1 here, down here. That's it. So what we got? And you have to find the angle between those two. That makes a parallelogram. That's right. Could be a new. This might be your life calling. You're gonna create a new exercise program, vector yoga. People will just get things like this and they'll have to go, oh yeah, this is the, yeah, make tons of money. I think it'll really be a hit. So there's our cross product. There's a picture of what's happening in 3 dimensions. You've got your parallelogram. And your cross product is -7, 30, -33. In order to find the cross product with the other formula, you would have needed the angle in between, which we weren't given in this question. We were asked to find that as well. So the Cartesian method here is much better for finding the cross product, and once we have that cross product, the area of the parallelogram is just the magnitude of the cross product. 45.144. When finding the angle between two vectors, even though there's a sine theta in the cross product formula and there's a cos theta in the dot product formula, the dot product formula is always better for finding the angle. Partially because with the cross product, when you have sine theta and it's positive, how do you know if it's in quadrant 1 or quadrant 2? How do you know if it's an acute angle or an obtuse angle with the cross product? But with the dot product, positive will be the acute angle, negative will be the obtuse angle. And when finding the angle between two vectors, you're never finding the reflex angle or the bigger angle on the outside. So our dot product is negative 55. The lengths are each there. Right, remember the dot product is just crashing corresponding elements into each other, adding up the pieces. And the dot product in this case is negative, so it tells us it's that angle in quadrant 2. Properties of the cross product. So you have to put a negative if you do it in the opposite direction. We've already talked about that one. You can, and this is typo. Does yours still say dot or did I change it on yours? Says dot. Okay. The cross product can be distributed. Now I don't know why you would ever want to. Because we just looked at the mathematics, like that discriminant thing or the IJK method. It's a little bit of work. How hard was it to add vectors? So easy. I don't know why you would want to double your work with cross products and then add them. Same amount of work in the end for adding, or add them first and then cross product. So I'm not sure why you'd ever want to do this, but you could. Notice though here, okay, when you've got a cross product, order, since order matters with the positives and the negatives, if I'm distributing a cross product after, all of my W's are after. If I'm distributing my cross product in number 2 here with the U before, all of my U's are before. So the order matters, just with positives and negatives. If the cross product is the 0 vector, and they're not 0 vectors to begin with, that means that your 2 vectors were parallel. And if you think of the cross product with UV sine theta, if sine theta is 0, that happens at an angle of 0, meaning if you put the 2 vectors tail to tail together, they've got to be exactly flat. So then they would be parallel. Now you might think 3 and 4 are like, Mr. JR, did you realize you wrote the same thing down twice? It's not written down twice. It looks that way, but in mathematics, this is saying that the first one says if the cross product is 0, then they're parallel. The second one says if they're parallel, the cross product is 0. It's important to say both ways because here's a very simple example of why you can't assume one thing backwards versus forwards. Okay? All horses have 4 legs. I have an animal in my house at home that has 4 legs. It must be a horse. It's a dog. Right? So just because all horses have 4 legs.
What? Shocking. I just was introducing Shanice Williams. She's gonna do our hairstyling next year. She used to be a student here and she's doing transitional math and business management. So we were walking by and I was like, so just walking by saying hi. Yeah.
see you again.
Yes, yes, I said we'll be her DH for
Yeah.
a second. Yeah, so anyways, just.
Okay, perfect.
But horses do have.
Yeah.
Still have four legs.
So a proof one way doesn't necessarily mean a proof the other way. But in this situation it does. Parallel implies the cross product will be 0. Cross product is 0 implies parallel. It works in both directions. And if you have some scalar in front, you could put the scalar in earlier to make your cross product math more robust. And you could put it in earlier with either one. However, I'd probably recommend keeping it out, do the cross product first, so you have smaller numbers to work with. So here we have 2 vectors. Use the cross product to show these vectors are parallel. And I'm not sure if the cross product is easier for showing parallel. Remember our old technique for showing parallel? Can you find a number that you can multiply this one by to get this one? -2? -2, yeah, yeah. Okay,
Hi, just doing an attendance check for Jonah.
yeah, Jonah's here, sorry.
Yeah, was he present?
Yeah, he's
Like, all
present.
along?
Yeah,
Okay, I'll just change it here. Thank
right,
you.
okay. Sorry, man. Who did I mark? Man, uh-oh. I marked, oh, maybe they changed it here, but I thought. Okay, you're marked present here. You were in your right spot. I don't know. Maybe the opposite happened. They thought you had leprosy and wouldn't be at school. And like, really? He went? I don't believe it. I've had to phone him. All right. So with our cross product, it would equal a 0 vector, so they're parallel. And here's this reminder. We could just use the scalar multiple. I still think that's the easier way of seeing 2 things are parallel. But maybe you were doing the cross product for something else and all those zeros appeared and you're like, oh, I guess it's parallel. And for those of you that have taken physics, here's another application of the cross product is to torque. Torque is the measure of force on an object which causes it to turn. So we apply torque to a nut if we put a wrench on it and push on the end. That's why we have more torque the longer it is, the more power that we have. So, there's your torque formula with vectors. Your torque formula is one vector cross product with the other one. In other words, it is the length of the one vector times the length of the other vector times the sine of the angle in between. For those of you in physics, did you use a torque formula? Did you have torque questions? Right? And so you just, the thing about physics, and I like physics, but generally what happens a lot in physics is they just bombard you with a whole bunch of formulas and then say, we don't care where those formulas come from. Or maybe they care a little bit, but they don't really show you all the intricacies of finding the formulas all the time.
Actually, Mr. Libby
He does?
typically does,
Okay.
but
Probably because they used to teach calculus.
Because he used to teach calculus. Perfect. I love that. But then after that, you're never expected to do that yourself. You just have to use all these formulas to solve stuff. Right? And that's the application. But now maybe we can understand this torque formula. Okay? And units for torque are Newton meters. So we have a wrench. Look at that beautiful picture I drew. It's 15 centimeters long. We have a force of 50 newtons that we're going to apply on the edge of that wrench. And we're not the smartest. We decide at an 85-degree angle. Smartest would be a 90-degree angle. Does that make sense? Have you ever tried the 0-degree angle on a wrench? As you put the wrench on, you just push as hard, and you're like, why doesn't it turn?
Because the cross product is 0.
Cross products, you're moving the whole whatever apparatus the thing is getting pushed away from you, but the nut is not turning. So 90 degrees, right there, I'm already telling you part B. 90 degrees gives you the biggest because sine of 90 is 1, which is the maximum for sine. The 85 degrees won't be bad. So what happens is we take our wrench vector, which I've done in black here at A, we take our force vector and put them tail to tail with the 85 degrees in between. The length of the wrench was already given to be 15. The force was 50. Sine of 85. And since the length, yeah, we have to change the length to meters because the units are Newton meters. So we need to make like this unit is in meters, this unit is in newtons. So when we multiply them together to get Newton meters, we have to make sure that our units were newtons and meters to begin with. If you left it as 15, I guess you could write it, your answers in Newton centimeters. And A cross F. We're going from A to F. Think about your toothpaste. If you righty-tighty, it would go inwards. So this, if it was a properly threaded nut and bolt, would tighten inwards. Now I always wondered if is that the, like, in physics, does this actually have an effect, that force being inwards? Is that why threads are normally in that direction?
sorry, you mean left-handed thread versus right-handed?
Yeah, does it act like, in my personal experience, it makes no difference. Like if they were opposite threads,
Yeah, I'm pretty sure it makes no difference at all.
right? But I wondered if, like in my head is like, oh, that force is in, does that have some sort of effect on?
Specific machines might call for something, but I don't know.
it's just like a standardization.
Yeah.
It's like a clock's all going one direction. The whole
So this is our little application of cross product in a formula you might have seen in your physics class. Okay, that's where we'll stop for today.